scientists reveal earliest evidence for shifting of Earth's crust. The puzzle pieces of Earth's rocky crusts are slowly and steadily moving, a process known as plate tectonics. These dynamic movements help to create the habitats and climate that fostered the emergence of life on our planet. But exactly when the geological process first emerged has been a matter of scientific contention for decades. Now, scientists say they have found the earliest direct evidence of plate tectonics on Earth, the only known planet to have the geological process. The findings suggest that the phenomenon was already shaping the planet billions of years ago. Why do you have mountains? Why do you have oceans? It only makes sense with plate tectonics, said Roger Fu, a professor of Earth and planetary sciences at Harvard University, who led the research for a new study that was published in the journal Science on March 19th. So, trying to understand when it happened on early Earth is a fundamental question. It makes everything else make sense, he said. Today, Earth's 7 major and 8 minor plates, which are on average 125 kilometers, about 80 miles thick, move at a steady rate of several centimeters per year. Each plate is in motion, either pulling away from or growing closer to its neighbors. And volcanic activity and earthquakes typically cluster at these margins. Some in the scientific community contend plate tectonics began 4.4 billion years ago, while others suggest they only started in the last 1 billion. Whether modern plate tectonics arose directly from the hellish magma ocean that once covered early Earth, or whether intermediate stages, such as plates that moved intermittently or one single unbroken lid, were at play is also unclear, the study authors noted. The latest research reveals the plates were shifting as early as 3.5 billion years ago during the Archean Eon, when the planet was already home to early microbial life. In pushing back the timeline for active tectonic plates, the analysis could offer clues about Earth's early history and the conditions that supported early life. According to the study, rocks capture Earth's early history. Fu and his colleagues analyzed rock samples from East Pilbara Craton, a geological formation rich with fossil evidence of early organisms such as stromatolites, in Western Australia's Pilbara region. If you don't get too close, it actually looks like really friendly, beautiful scenery because it's got these low rolling hills. But once you start walking around, you realize it's full of very spiky grasses with sharp tips, he said. For their study, Fu and his colleagues harnessed a phenomenon called paleomagnetism. Magnetic minerals within rock record the inclination of Earth's magnetic field lines at the moment they form, allowing scientists to infer the rock's original orientation and latitude. Our job was to basically measure these grains and see what the magnetic alignment of these rocks was, Fu said. You can take the angle between the observed magnetic field direction and the horizontal, and you can say, are you near the poles or are you near the equator? He explained. By analyzing 900 rock samples collected from Pilbara that represented a 30 million year time frame, the team found that part of the formation shifted in latitude from 53 degrees to 77 degrees, a drift of tens of centimeters annually over several million years, and rotated clockwise by more than 90 degrees. The researchers also assessed existing paleomagnetic data from the Barberton Greenstone Belt in South Africa, which was nearly stationary at a lower latitude during roughly the same period, according to the study. By looking at the two sites, it was clear that the lithosphere, which comprises the Earth's crust and the uppermost mantle, was not a big, unbroken shell across the globe, as a lot of people have argued before. Lead author Alec Brenner, a postdoctoral associate at Yale University, said in a news release. Brenner conducted the research as a doctoral student in the Department of Earth and Planetary Sciences at Harvard University. Instead, it was segmented into different pieces that could move with respect to each other. The findings are highly significant, mainly because they represent a huge amount of high-quality paleomagnetic data that's uncommon for such old rocks, said Ucursia, a research fellow at Curtin University in Australia, who was not involved in the study. The important outcome from the research, you noted, was the indication of relative motion, with data revealing movement in the Pilbara Craton and the Barberton Greenstone Belt largely remaining stationary. This is crucial evidence of how Earth transitioned towards the plate tectonics world, he said.